All right, engineers, in this video, I'd like to do some practice looking up the properties of water using the steam tables in the NCEES handbook. You can get your own copy of the NCEES handbook. I'll put a link in the comments where you can download it for free. I'm going to be working through these 6 examples on this worksheet, and I'll put a link to this worksheet in the comments too if you'd like to follow along or try it and then come back to the video if you get stuck. The first thing I like to do when I'm working through these problems is I like to draw my location on the property plot, and that just helps me. It's like drawing a little map. So this is like a PV diagram, and I usually draw the steam dome on there, and then I also usually draw an isotherm on there, at least one. That just kind of helps me figure out where I'm at on the map. And so in this case, this would be the 50 degrees Celsius isotherm. And my state is given, the quality is given to be 0. So I know I'm going to fall right over here on the map on that saturated liquid line. And so I can go ahead and start filling this out. This is a saturated, I'll just write saturated liquid. And then I can look up the values at 50 degrees. I'm going to go over here to my table and look here. I have my 50 degrees. The saturation pressure is going to be 12.3 kilopascals. And I can read these values for saturated liquid. So I have the saturated liquid values over here. And I can read that value. It's 0.0, whoops, right in the wrong spot here. 0.001012. And I can also look up the internal energy for that saturated liquid. It's 209. I'm going to be a little lazy with my sig figs in this video. Okay, let's move to a harder example. So this next one is 100 degrees, and it gives me the internal energy. So again, I like to draw my map. I'm going to keep doing a PV diagram here. I'm going to draw my dome on here, and I'll draw my 100 degree isotherm on there. And I'm going to scroll down to 100 degrees. And now I'm going to look. I have my my internal energy at 100 degrees. If it's a saturated liquid, it's going to be 419. If it's a saturated vapor, it's going to be 2,500. And I'm at 1,500, so I know I'm somewhere in between the saturated liquid line, which would be the left side of that dome, and the saturated vapor line, which would be the right side of that dome. I'm somewhere between there. So if I draw my point on the map, I'm in that saturated liquid gas mixture. So saturated liquid gas mixture. And I can go ahead and I can look up my value here, my saturation value on this table. It's 101 kilopascals, 101 kilopascals. I'll need to calculate my quality in order to get my volume. And so the equation that I'll be using is, I know that U is equal to UF plus my quality times UFG. And I can look up those values of UF and UFG on the table here. So I'll just highlight those. I can look up those values right there. And I have my value of U. It's over here, that 1,500. And so I could solve that for X. And if I solve that for X, what I get is my quality is 0.52. The ratio of vapor by mass to liquid by mass is it's 52% vapor. Then I can use that quality. I can plug that into the same equation over here. I know that V is equal to VF plus X times VFG, but VFG is not given in those tables. And so I need to use VG minus VF. That's the definition of that. And I could plug in those numbers. I can look up VF and VG, the volume of the saturated liquid and the volume of the saturated vapor, and I could plug those in and get my specific volume, 0.867 meters cubed per kilogram. Perfect. moving right along to this next example here, we're going to get, again, always draw my map. This time I'm going to draw my isotherm, and I'm not going to label it quite yet because I don't know what my temperature is, but I do know my pressure is given at 200 kilopascals. And so let's scroll down here. Now I'm looking at these pressures on this table, and I get down to a pressure of, whoops, went too far. Right about here, that's pretty close to 200 kilopascals. For most of the problem solving that we'll be doing with the sig figs given, that's going to be fine. So I'm going to go ahead and write that the temperature is 120 degrees Celsius, and this is a saturated vapor. I'm over here on the dome, and so this is my, now I know it's my 120 degree isotherm. I'm on that saturated vapor line, and I can plug in these numbers here. So I have 0.89 is my specific volume. My internal energy is over here, 2,529 kilojoules per kilogram, and this is a saturated vapor. All right. These examples are going to get a little bit harder. These last two are going to be some special cases that I want you to be aware of. This one is given 800 kilopascals. Again, I'm going to draw my dome. We're over here at 800 kilopascals, and we again don't know our temperature, but the internal or the specific volume is given 0.32. So if I go down, if I scroll down to about 800, somewhere right around here, and look at the specific volumes, so the specific volumes are in this column right here as a saturated vapor. I could see that these specific volumes are both lower than the specific volume I have. So over here in my diagram, I know that at that pressure, I'm going to be somewhere over here to the right of the dome. And that means I'm in a, we call that a vapor, or sometimes we'll call it a superheated vapor. I'm outside of the dome. When I'm outside the dome, the quality doesn't make any sense. The quality only makes sense when I'm inside the dome, so I don't need to fill that in. And I also now know that I need to go to my next table. I need to go to my superheated water table on the next page to look up the values for this. So I'll go down and find 800 kilopascals, that's 0.8 megapascals, and I'm going to look for this volume. So volume is in this first column here. I'm going to look for that volume that corresponds to the number that's given to me. So this is going to be, let's see, 3.3241 is that row right there. I can look up the temperature now. It's 300 degrees. And I could fill in the internal energy, that second column, 2,797 kilojoules per kilogram. One thing to note is that if I go back to these rows here, this isotherm that I drew that goes across A800, that falls at 170 degrees about. And this point I drew is above that isotherm. So I know that the temperature should be hotter than 170 degrees. And indeed it was 300 degrees. All right, last one, 200 degrees Celsius and 2,000 kilopascals. So I'm gonna draw my map, my PV diagram, and draw my dome, and draw my isotherm on that dome. And I'm gonna look up what at about 2,000 kilopascals, that's 2 megapascals, what my saturation temperature is, and look at these values here. If I go to, let me just go to 200. The pressure is less, the saturation pressure is less than 2,000 kilopascals. So what that means is that I'm going to be over here I'm at a higher pressure, right? This value that I'm looking up is 1.5 megapascals, and my pressure is over here at 2 megapascals. So I'm going to be over here on the left side of the dome, outside the dome. So again, quality doesn't make any sense. This is liquid water because of that high pressure. Liquid water, sometimes it's called a compressed liquid. And some textbooks have tables for compressed liquid water. The NCEES equation book doesn't. But to look up these values, I know that my volume, my water is roughly incompressible. So my specific volume should be about equal to that value given at that temperature. And also internal energy is going to track closely with temperature for liquid water. And so I could just pull both those values out, and those are going to be good guesses. So 0.001157 meters cubed per kilogram is my specific volume, and my internal energy is 851. So that gives me a kind of a wide range of cases. I always kind of draw my map and then kind of work to figure out where I'm at on that dome so I can go to the correct table and get those values. In my next video, I'm going to do some examples where we might have things that don't fall neatly on the table. We might have to interpolate between two values, and so I'll do an example of linear interpolation in my next video. Thanks for watching.